The adjacency matrix representation of a graph G requires time and memory, because when we represent in computer memory, we always think about how much time we need to um, to spend to enter data into the matrix, and how much memory. So that's why, and here I just give you a formal approximate idea about the amount of time proportional to the number of vertices squared. Here number of vertices 4 and 4. The number of position is 16, and that's it. So we have to enter 16 positions. Uh, and also it is time and memory, because we must have so many variables in the matrix. Same is here, same is here. A graph can be presented in computer memory by an array of adjacency lists. Array of adjacency lists. Or we can forget about array, but just say by adjacency lists. Elements of such an array are indexed by vertices. Each array element, number j, contains a pointer or reference at a list of vertices adjacent to vertex v sub j. An adjacency list, so have a reference, a link to adjacency list for vertex v sub j. Typically, each adjacency list is a linked list with pointers into dynamic memory. For example, adjacency list for G1, vertex A, and he is adjacent to B, is adjacent to C, is adjacent to D. List of vertices that are adjacent to A. List adjacency list for vertex B, AC, ABD, BAC. Okay, and here adjacency list for graph G4. An empty list for vertex A, vertex B is adjacent to. Oh my God, it is not good to mention like that. Just a moment. Excuse me. I did it in hastily. Look, G4, it is weighted. And if I make a list of adjacencies like this, then we don't see that it is weighted. That's why near each B, A, 12, C, 9. 12, and here 9. C, from C to D, 5. and from B to A, 7. It should be like that. Representation of a graph G by its adjacency list requires time and memory both in E sub G proportional to the number of edges in the graph, because here one edge, another edge, one edge, and here edge, edge, edge. So proportional to the number of edges, and here proportional to the number of vertices squared. A graph can be formally represented by many other methods, We shall discuss some of these methods when they are required by an algorithm that process or work on the graph. The operation of a graph algorithm is greatly influenced by the method of graph representation. Here, I give you just only 2 basic methods, and here even it is given in the list of adjacencies in an abstract way. It doesn't give any details of memory representation in computer memory. Here we just say A is adjacent to BCD. That's it. But how to actually represent it in computer memory so that we can work with this list conveniently? Nothing is said. We'll discuss it in another course, algorithms and data structures. Okay. Now, people, do you have any questions? Did you study graphs at school or at some previous?
No.
No. I assume no. Well, thank you.
Yes.
Of course, some of you yes, some of you no, but at least some of you know, because it would be a pity if I told you only what you already know. Okay, but now, what did, I will start, I have to start talking, where is it? Stop. Next. Or okay, group number 1, 2, and 3. Do you see this title, Lecture 11 Trees?
Yes. Yes.
You do. Okay, now I do same thing for another. People in groups 4 and 5, do you see this lecture 11 trees.
Yeah, we do.
You do.
I
Okay.
do.
Very nice. People, thank you for your kind attention. Now, let's make a break. Because it is 12, I need to drink some tea. Oh, and we'll
Good appetite.
start exactly at 12:05. 05. Okay. Have a break. Oh, before I go, I wanted to ask you, how about your labs, people? If there are any people who did not submit lab number 1 to the teacher of labs, to Gleb.
I actually have not.
Sorry?
I have not submitted 2 first labs.
Two first. And what about the third one? Okay, two first you did not. Okay, is it so difficult or because you are so busy? Why is that?
No time.
No time. Oh,
We don't have enough time to check all people at one lab, so
you
many
see,
didn't pass.
the teacher doesn't
Yeah,
have enough
yeah, yeah,
time to
yeah.
talk
Yeah,
to each of the students.
it takes too much
This is
time to check one student, so others
I see.
are
I
not
see.
checked.
I see. Mhm. Thank you. So, by the way, before I forget, today after this lecture, I don't have other class for foreign students. That's why uh, I can make a consultation. Actually, I want to find out what is the situation with these labs because it looks that the teacher uh, in also was unwell in labs also was unwell. That's why not only time but also energy. You need energy to discuss it. That's why I want to know how many people, approximately at least, already submitted and how many not. How many not? Okay, thank you. Have a break. Oh my God. People, I of the groups 1, 2, 3. 1, 2, 3.
Yes.
Do you see?
Yeah.
No. These lecture trees.
No. No.
No, you don't. You don't. That's why.
No. Yes.
Okay. Now, people from group 1, 2, 3, do you see this lecture 11, 3?
Yes. Yes.
Yes.
Yes. Yeah.
Now, just a
Yeah.
moment. Just a moment. We come here. Because one little move and you have to adjust everything from the very beginning. Now, people, group 4 and 5, do you see lecture 11 trees?
Yes.
Oh, you don't?
Yes.
Well, I didn't understand. People, groups 4 and 5, do you see these
Yeah, we can see.
lecture trees? You can see. Very nice. But why?
It disappeared from the first.
Disappeared. Yes, because now I see stop sharing only one little thing. Yes, oh my God. Okay, let me see. Here, 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 here. To share. Now, 1, 2, 3. Do you see lecture 11?
Yes. Yes.
And group 4 and 5. Do you see lecture 11? Well,
Yes.
at least
Yes.
yes. Okay. Now let's continue. Trees. Trees are special types of graphs. Special types of graphs. Tree vertices are often called nodes. An undirected tree, or just tree, is an undirected, connected, acyclic graph. So, a tree is an undirected, connected, acyclic graph. An undirected graph is an undirected, disconnected, acyclic graph. Connected components just sorry, an undirected forest. So it was a tree, just a tree, connected acyclic graph. Undirected forest is undirected, disconnected, acyclic graph. Connected components of a forest are trees. For example, this is a picture of undirected tree. And the number of pictures, you can read it in more detail in the manual that you have in a sufficient number at the library. But I decided to copy it from the book so that you can, now it's not the time to visit libraries. So this is a tree. And here, undirected, disconnected, because here we have three components, one component, two component, three component. And each connected component is now called a tree. A tree. An undirected tree may represent, when we can use such an undirected tree, a map of two-way highways connecting towns. If each vertex represents a town, and these are two-way highways, roads. A molecular structure, if atoms, and here some atomic links or something, an electrical circuit, etc. Here are some features of an undirected tree. T, which is a pair of vertices as usual for graphs, V sub t, E sub t. Number of vertices is one greater than the number of edges in a tree. If you count here, 1, 2, 3, 4, 5, 6, 7, 8. 8 edges, and how many? Is it 8? Yeah, 8 edges, and how many vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Any two nodes are connected by a single path. You take this vertex and this, and there is a single path connecting them. This and this, single path. If any edge is added, for example, from here to here, then there will be one cycle, exactly one cycle will appear. It will be op, if edge one here, op, and op, one cycle. We add it here. Immediately, exactly one cycle is added. A rooted tree is a directed tree. So some trees are rooted. A rooted tree is a directed tree with a special node called the root. The tree root is the node that appears first, that gives the origin to other nodes in a tree. In a rooted tree, the tail of every directed edge is called the father node. So if it is a node of a tree, and the direction of the edges here, then this is the father, this is the son node. A binary tree is a rooted tree where every father node has not more than two sons. And now here, no directions, that's why no no father and son relation. And but if every father node not more than two sons, then one son is called the left son, and another son is called the right son. Most algorithms for binary trees are recursive. Since the nature of a binary tree itself is also recursive. Algorithms for binary trees are recursive because, or since, a binary tree is, its nature is recursive. A binary tree is a finite set of nodes. I give you now a recursive definition of a binary tree. A binary tree is a finite set of nodes which is either empty or is partitioned, divided into three disjoint subsets. So we don't even mention here any edges, set of edges or something. Set of nodes, a single node called the root. A subset of nodes called the left subtree, which is either binary tree itself. A subset of nodes called the right subtree, which is a binary tree itself. Okay, so here is a picture of a general rooted tree. This is the root node. It has three sons. This is the father for E. C has no son nodes, and vertices without sun nodes, they are called leaves. One leaf and many leaves. And this is a productive pattern for making a plural number of a noun. You remember leaf, leaves. A calf, calves. A hoof, hooves. And well, I don't now remember, but very often it is presented, created so. So in tree T1, the root node A, father node for sons A, B, C, D. The node C has no sons. Its degree is equal to 0. In a tree node with no sons, a leaf. A node with no sons is called a leaf. And T1 contains such leaves, E or leaves. In a binary tree, each son is either left son or right son of E, left side or right son of H. Okay, but now I gave you here a recursive definition of a binary tree. Now, look, here we have how many? 5 vertices. These vertices are partitioned or divided into 3 subsets. One subset, O, which is a root. Another subset, which is called the left subtree of the root H, which is a binary tree itself, and the another set, which is a binary tree and is called the right subtree of H. Now, but if it is a binary tree, then it is also divided into a root and into a left subtree, a set of left nodes which make the left subtree of I, and set of nodes which make the nodes of the right subtree of I. Here, the left subtree, again, it is partitioned into such subsets: root, and the left subtree is empty set of vertices, and the right subtree is empty set of vertices. That's why when a subset of vertices becomes empty, the recursive decomposition ends. We reach the base case, because which is either empty, and that's it, we stop. Or if not empty, we continue dividing. We reached which is empty, we finished. Same here. Root, empty, empty, finished, everything here. After that, we make decomposition of this right subtree of H. Root, empty tree, empty, empty left subtree, empty right subtree, and that's it. So also we said that it is a directed tree, but here we don't see any directions of edges. But in any binary tree, edges are assumed to be directed down from the root. And the nodes are placed in levels. The root belongs to level 0. Sons of the root node belong to the level 1. Sons of the sons belong to level 2, and so on. Directions of edges is not specified. In any binary tree, edges are assumed to be directed down from its root to leaves. T2 can be specified as a general graph also. T2, set of vertices, here 5, and set of edges, H sub I, H sub J, I sub K, a set of edges. But you will see that it is such a presentation of a tree is not always convenient for processing a binary tree by algorithms. So here I showed on the picture, and here I wrote T2 root H, 1 left subtree I K L, right subtree J, and so on. After that, decomposition until we reach left and right subtrees become empty. Now here we stop decomposition. In a binary tree, the level of a node is defined as the length of the path from the tree root to the node. From the tree root to the node, the length of the path is 0. Okay, 0. The length of the path from root to this is 1. That's why level 1, and so on. The maximal level of a node in a binary tree, the maximal level of a node in a binary tree is called the depth, or the depth, also the height of the binary tree. Well, there are, because we may specifically define the height of each node and so on, but it is the number of nodes. The height of this node is 1. 1, it is the number of edges connecting this vertex with the root. It is the height. Okay. in a binary tree with exactly 2 to the power level nodes at each level is called a complete or a full binary tree, where level numbers are 0, 1, 2, depth. For example, here, root, level 1, level 2. At this level number 0, we have 2 to the power 0, 1 node. At level 1, we have 2 to the power 1, 2 nodes. At level 2, we have 2 to the power 2, 4 nodes. And here that's it. And this is the depth. It is the maximum level of the node in this tree, level 2 depth. Okay. It has the minimum depth d among all binary trees with the same number of nodes n. It is in a full or complete binary tree. Full or complete binary tree. All leaves are at level number d, depth. All leaves here. The number of nodes is equal to, 2 to the power d plus 1 minus 1. So d, depth, is 2. That's why 2 to the power 2 plus 1, 2 to the power 3 is 8, minus 1, 7, we see it's 7. And also, in the complete binary tree, the depth is equal log base 2 of the number of nodes. Here 7. Here 7. Log base 2 of 7. Do you know what is it? Log base 2 of 7. We know that it is greater than log base 2 of 4 and less than the log base 2 of 8. Log base 2 of 4, 2. Log base 2 of 7, 8 is 3. That's why the value of this log is somewhere in between 2 and 3. So 2 and fraction. And this is a symbol of a floor function that discards any fraction in this log, if any. That's why 2.7 or 5 or 9, it doesn't matter. It is discarded and we get 2. And the depth is 2. Okay, so these are interesting features of a complete. Sometimes such a tree is called a perfect complete binary tree. And such a tree with some nodes at the bottom level missing, they are also considered to be complete. But we'll meet with such a case in the course of algorithm and data structures when we speak about heap data structures and heap sort algorithm. Okay. A method of a representation of in memory depends on the tree type. There are many methods. And the algorithm for processing the tree. A general tree, directed or undirected, can be presented as any graph by its adjacency matrix, list of adjacencies, etc. A general tree. If every node may have, well, many adjacent nodes, not sums. 3, 5, or something directed on. A binary tree, now it is directed and so on, is often represented by dynamic nodes. Dynamic nodes linked via pointers, references. Well, dynamic nodes. What do you know what is dynamic? Huh? Not in relation to nodes, but dynamic in general. What do you mean? Dynamic. It is changing in time. Changing in time. Dynamic nodes, they are created when the program runs, not declared at the stage of compilation or something to be allocated memory by a compiler. No. Dynamic nodes are allocated memory when the program is running, and they are allocated memory by the operating system at the request of the program. And they are linked by pointers or references. For example, the memory for tree 2 for this. Representation for binary tree 2 can be viewed so: one node with a value of h, the root h, and left sun I, j, after that k, l. So here a pointer to the root with data about the left sun of h. And here in data part we have I, a pointer to the left sun of node with I. It is node with k. And there are no left and right sums. That's why special values of pointers, null pointers, that indicate, well, that there are no links, no more nodes, end of recursion, end of recursion. And here, like that, and like that. Well, here, I just present it as looking as a tree structure, but in memory, of course, it is a sequence, some in random access memory, and somewhere this node is given the memory by the operating system. This memory is given the memory maybe before this one, maybe after that one, where the operating system finds memory. And this address will give access to this node, and so on. In physical memory, there is no predictable sequence of these nodes, arbitrary sequence. But we can travel from node to node using this point. Symbol 0 denotes zero value of a pointer or reference. Such a tree object. Oh my God. Here, well, such a tree object consists of two parts. A pointer, a special pointer, that will give access to the root node, and a necessary number of nodes placed in dynamic memory by the operating system. So, but I will not go any deeper here because you did not study object-oriented programming and so on. Well, let it be. Just a tree may be represented as collection of nodes linked. This node is preferable of representing trees is preferable if a binary tree is processed by some recursive algorithm, because each node is a root of another binary tree. This node is a root of another binary tree. Such a representation requires some extra memory for pointers here. For pointers. Not all algorithms for binary trees are recursive. That is why other methods are also used for representing binary trees. For example, a heap, a special type of a binary tree, is conveniently presented by an array. We shall discuss this method later in relation to heap sort. Also, well, here is another method to represent formally a tree by a code, sequence of numbers, tree code, an arbitrary tree, binary or not binary, directed, meaning rooted or undirected, can be presented by its tree code, which is a sequence of node numbers. So, node numbers. If a tree contains n nodes, then the code contains n-2 node numbers. The code contains n-2 node numbers. Well, here is a picture of a tree. Here no root. It is not a binary tree, but at least, look, nodes are numbered from 1, 2, 3, 4, 5, 6, and 7. 7 nodes. And we'll use this tree to understand how we create such a code. Algorithm for tree coding, and numbers are marked with numbers 1, 2, and so on to n. Here, 7 numbers, 7 nodes, and numbers from 1 to 7. First, find a leaf with the minimum number and delete it from the tree. Find a leaf with the minimum number and delete it from the tree together with its adjacent edge. Well, adjacent edge. Maybe it is not a good idea to call it adjacent, because the relation, well, I will put here look, it is the relation between the adjacency. It is relation between vertices. Two vertices connected one edge, they are called adjacent. But the relation between the edge and its vertex that makes this edge is called the relation of incidence. Vertex is incident to the edge. Edge is incident to a vertex. But this I found in the book. That's why maybe it is also possible to call that the edge and the vertex are adjacent. Well, doesn't matter. You understood it. With each adjacent edge or incident, if you want to be strict. In this picture, deleting an edge is denoted by such, denoted by a short solid line. So look, these are leaves. What is a leaf with a minimum number? It is 3. We delete it together with the incident or adjacent edge and enter the number of the node adjacent to deleted one into the code. Look, after I delete it, 2 is entered into the code first. Now there is no anything. Repeat step 2 and 2 times. Now, and 2 times. Now we are searching for a leaf with the minimum number, which is 4. Delete this leaf together with the incident or adjacent vertex, edge. And after that, we write 1 into the code. Okay, now we have leaves here, here, and here. The leaf with the minimum number is 5. We delete it together with the edge, and we write the vertex adjacent to deleted one in the code 2. Now we have, what is it that we have? A vertex, leaves 5 and 7. 5 and 7. No, I mean 6 and 7, because 5 I already. 6 and 7. We delete 6 together with this one, write 1 here, and now we have 1 vertices which are left in the tree. 1, 2, 7. Now a leaf with the minimum number is 1. 1. We delete it together with the edge and write 2 here, 2 here. We deleted n minus 2 vertices, and the code has the length n minus 2, 5. This is the code. We stop it. We stop it. Now, but coding is useful if we can restore the coded information, if we can restore the tree itself, Oh, people, before I forget, I hope you did not forget to register your attendance, eh? Of course, great. Now, how do we restore the tree if we given the code? Restoring tree by code. First of all, we have tree code 21212. If so, the here n minus 2 numbers, 5, the total number of vertices in the tree or nodes is 7. Here they are, list of nodes, 1, 2, 3, 4, 5, 6, 7. Okay, algorithm. How do we connect. You can notice that node numbers 3, 4, 5, 6, and 7 from the list are absent from the list, are absent in the code. So they are leaves. Well, but forget about it. Well, now look at the algorithm simply. Connect the smallest number remaining in the code remaining in the list of vertices, the smallest number, which is absent in the code. 1 is not, it is present. 2 is present, but 3 is absent in the code. Delete the connected 3 and 2 from the list. After that, repeat step 1 until odd code numbers are connected with list numbers. Now here are the steps. List of nodes 1, 2, 3, 5, 6, 7. Code. These 2, 1. So we delete, connect 3 and 2. They are already excluded from list here and here. Now we have 1, 2, 4, 5, 6, 7, and here 1, 2, 1, 2. Again, search the smallest number here, which is absent here. It is 4, and connect it with the first in the code. 4 and 1. Okay. Now, after we deleted them and connected them, we are left a list of nodes 1, 2, 5, 6, 7, and here 2, 1, 2. Now we are searching for the smallest number here, which is absent here. It is 5. We connect 5 with the first number in the code remaining. In the remaining code, 2, 5. Okay, now 1, 2, 6, 7, and here 1, 2, 1, 2. We're searching for the smallest number here, which is absent here, 6. It is 1, 6. These are edges, by the way. These are edges of a tree. Finally, we remaining nodes in the tree 1 to 7, and the code 2, the smallest number here 1, which is absent here, we connect 1 and 2. After that, we have only 2 and 7. 2 and 7. We connect them, connect the remaining 2 numbers of the list, 2 and 7. That's it. If we build the picture and connecting 3 and 2, 4 and 1, everything in one picture, we'll get the same tree, maybe of a bit differently shaped, but the connections are the same. For example, here 1, 6. Do we have 1, 6 here? 1, 6, 1, 6. Where is it? Here 1, 6 here. We found it. And okay, people, we have 1 minute left. I think it's time to stop. And those who have questions, want to continue, you are welcome for the consultation at 1:10. 1:10. Now, do you have any questions, please, people? Ask me.
No.
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 In this case,
No.
thank you, very kind of you. I just Stop recording. I stop it. Stop here. So, see you later.
See ya.
See you later.